Thank you for the introduction. Thank you for coming tonight. It's a real pleasure to be here. I want to talk to you about some of the fascinating engineering challenges that we've faced in the development of the Curiosity mission. So here by a show of hands, who knows what the Curiosity mission is? Okay, good. Good studying ahead of time. And the picture that you see here on the initial slide is actually a selfie that Curiosity took of itself on the surface of Mars. And people ask, well, how can it do that? It has many different cameras and also has an arm which can go around and piece together the pictures and take a 360-degree view, just like we could do here by taking a picture of you. The other thing which is of interest is that you can see the surface of Mars right here, and you can see several different craters on the surface of Mars, and we landed Curiosity in one of those craters, a crater known as Gale Crater. So I'll talk a little bit about the challenges of landing on Mars and the challenges specific to the element that I worked on, which was the supersonic parachute. We have some demos and materials to show you as well. In terms of giving you a little bit of background about myself, I'm actually originally from the United Kingdom. I was born in Glasgow. I have no accent now because I moved to New York when I was a small child. But I spent, I guess, the first 2 to 3 years of my life here in the United Kingdom. And then moved to the United States, which is where I did all my education and my schooling and where I now currently work. In terms of my story, another British aspect is that when I was growing up as a child in New York, I watched an amazing science fiction program on public television known as Doctor Who. And ever since a small child, since the age of 6, I watched these reruns, and my doctor was Tom Baker, actually. And I was so fascinated by this alien who actually had the ability to solve all problems by using his brain, right? Using his willpower, his brain, his compassion, and his humanity, even though he wasn't human. And so growing up, I felt as though that was a wonderful influence for me, and I actually aspired to be able to be something like him, which was a scientist, an engineer, a brilliant person being able to solve the challenges. And so that's kind of what motivated my interest in engineering and in space exploration. So that's kind of an interesting aside, and I'm still a huge Doctor Who fan today, and I attend conventions in the United States on the topic. But I always knew I wanted to be involved in the space program. And so what I selected was to be an aerospace engineer, and so I studied aerospace engineering for my undergraduate degree, and then I continued to do aerospace engineering for my master's and my PhD, and I did that out in California. And over the course of my career so far, I've worked for NASA for around 15 years, I've been able to work on a variety of different projects. The very first one was developing something called ion engine technology, or plasma propulsion. So my background actually is rocket science. That was also something I wanted to do growing up. And so we developed engines which are now powering the Dawn spacecraft. So if any of you are familiar with Dawn, there's 3 very high-precision, low-thrust, but high-efficiency engines which have taken our spacecraft from Earth to the main asteroid belt, looking at 2 very unique asteroidal objects, one Vesta, one Ceres. After I worked on the development of ion engines for several years, I decided to do something completely different. I was asked if I wanted to work on the next mission to Mars, which was the Mars Science Laboratory Curiosity mission, and if I wanted to develop the supersonic parachute. And to me, that was an opportunity I couldn't refuse. How could you not want to work on a mission to another planet? So I did that for about 5 years. And that was successful. And then I decided to move on to a different challenge, which is my current challenge, which is developing a scientific facility for the International Space Station, which is going to launch in just under 1 year, actually. And so that's my career path. And what's so amazing about engineering for the students in the audience, or for the parents with students, is that with engineering, you can kind of do whatever you want. You take the tools of math and science and create new technologies to solve the world's problems, and in most cases, advance humanity. So that's the reason why I think engineering is a wonderful profession. It's a wonderful degree for anyone to obtain, even if you choose to do something different beyond that. So that's a big plug for the field of engineering, whichever one that may be. But what I wanted to start off tonight is to talk about how it was so difficult for us to be able to land a rover, basically the size of a small car, on the surface of Mars, which is billions of miles away. And so obviously I'm a little bit biased since I worked on it, but it was probably one of the most fascinating engineering feats in the past couple of decades. And so we've been successfully driving the rover around on the surface for the past almost 4 years now, collecting science data. And I'll talk a little bit more about the rover mission in terms of what its science is and what it's collected to date, but I wanted to focus a little bit more about the entry, descent, and landing second, and also why is it that we explore Mars. And so the obvious question to ask is, why are we interested in Mars? And the picture that you can see behind you is obviously Earth is on the left and Mars is on the right. And they look incredibly different from each other. But what's fascinating is that when the solar system first formed, planetary scientists actually believe that Earth and Mars were very similar to each other, both in terms of having a thick atmosphere and also having water on the surface. But over time, the two planets have evolved very differently from each other, where Earth still has a very thick atmosphere, it's almost 3/4 covered in ocean, whereas Mars is very dry, dusty, a very thin atmosphere, and no appreciable water on the surface. So why is it that these two planets evolved so differently from each other? And also, by comparison, Venus, which is one planet in from us, which also has a very similar initial composition and size to Earth, is completely different. Venus, on the other hand, is around 470 degrees C on the surface and has 100 atmospheres of pressure on the surface. So on one hand, one planet in, you have essentially what is like the inside of a self-cleaning oven, and one planet out, you have something we couldn't survive on. And so the way we can understand how the planets evolve is actually by sending spacecraft there. Spacecraft to orbit around the planet, and then also spacecraft that deposit landers and rovers to explore and make scientific measurements of the surface. And so that's the reason why we explore Mars from a scientific purpose. But the second reason, of course, is that at some point in humanity's future, we're going to want to live on somewhere other than Earth. And Mars is actually a relatively nice place. So we want to be able to learn as much as we can relative to other places in the solar system. But we want to be able to learn as much as we can about the planet from a scientific perspective, so we can understand what the properties are on the surface, what the composition is like, can we possibly access water, what the radiation environment is like. But we also have to develop the engineering technologies to be able to land a human-sized payload on the surface of the planet, as well as technologies to be able to survive on the surface of the planet. So those are the two reasons why we explore Mars. But first, I'll test some of your knowledge of as would we one day live on Mars. So who thinks that the day on Mars is shorter than the day on Earth, by a show of hands? Longer? Slightly longer, yes, you're right. So it's a little bit longer. It's 24.6 hours, which means from a human circadian rhythms perspective, it wouldn't be that challenging to be able to acclimate yourself to a slightly longer day. And actually, our engineers at the Jet Propulsion Laboratory who operate the rover do just that. They're always shifting their time in terms of going from 24 to 24.6 hours in terms of what their operational shift is on the ground. Now, in terms of gravity, who thinks the gravity on Mars is higher than on Earth? By a show of hands, lower? Yes, it is lower. It's about 1/3 the gravity of Earth. And the reason for that is that the planetary body itself is much smaller, therefore the gravitational force, the gravitational attraction, acceleration is much lighter. So even though 1/3 g isn't good for a human body to be able to deal with, it's still much better than 0 g that, for example, we have on the International Space Station. So from a human physiology perspective, it's also relatively more sustainable for us to be on Mars versus on our moon, which is even smaller with 1/8 g, or in basically essentially in free fall if you're on the International Space Station in the vacuum of space. Now, from a temperature perspective, the temperature on Mars, although it is cold, especially in the nighttime, in the polar latitude regions, in the wintertime, it actually does get relatively warm. 5 degrees C is actually a very common California winter, for example. So from a temperature perspective, it's also much better to be on Mars than in the vacuum of space or on our moon. So for these reasons, actually, it's not a bad planetary body to think of for future colonization of human beings, for example. Now, the big problem with Mars, of course, is that the atmosphere is very thin. It's only about 1% of what the atmosphere is here on the surface of the Earth, which means that if we do live there one day, we would have to be in a pressurized environment or pressurized suits for the surface of the planet. And then, of course, the atmosphere is not made out of air, which is primarily a mixture of nitrogen and oxygen, but it's made out of CO2, and we can't breathe CO2, so if we do in the future go to Mars, we would have to either come up with a way to turn CO2 into oxygen by splitting it up or bringing our own oxygen supply with us. But in terms of a future destination, for these reasons, Mars is feasible, it is practical, and it's also the closest planet to us. So then the challenge becomes being able to land something on the surface and be able to survive on the surface for extended periods of time. I think they wanted me to take questions at the end, but I'll take your one question now. So go ahead.
Bacteria which were adapted to the cold and were photosynthetic, which could potentially make the atmosphere into some oxygen.
That's a really good idea, and that is like a terraforming approach. So if you were able to bring bacteria with you or plants which took in the CO2 and created O2, that would be a way to actually self-create your own atmosphere. So that's a great idea. And so that's something which would be a type of terraforming that you could do. But that's actually a fantastic idea. So If I go to the next slide, however, is thinking back to the geological history on Mars. Mars actually had a very, very ancient geological past. And the picture that you see on the upper right, Olympus Mons, is an extinct volcano. And it's actually the largest volcano in the solar system. So who thinks it's twice as high as Mount Everest? 3 times as high? It's actually, yes, 3 times as high as Mount Everest. And the reason for that is because at some point in the planet's past, it did have a lot of volcanism. But now that volcanism appears to have stopped or doesn't appear to be present, and we don't really understand why. Perhaps that's correlated to the reason why the magnetic field was lost, why the atmosphere is lost, we don't know. And so we send spacecraft to make measurements to be able to answer that question. And that's actually one of the primary reasons for the InSight mission, which is launching in 2018, which is actually going to carry on board a seismometer to make measurements of Mars quakes, if there are any still present. Another fascinating feature is the picture that you see on the lower left, which is Valles Marineris. It's actually a scar that goes across the center of the planet. And we like to talk to it as being Mars's version of the Grand Canyon. And it's an impressive feature. It's actually roughly 6 times as deep as the Grand Canyon. So what this means is that at some point in the past, there were appreciable water flows on the surface, but now they're gone, and we don't know why. Was the water completely lost? Was it stripped away and taken off into space? Or is it still frozen in the subsurface or in the polar regions of the planet? And the way we can answer those questions is, once again, by making measurements on the surface of the planet, which we have been doing. So who thinks that Mars has moons, by a show of hands? So Mars actually has 2 moons. It has Phobos and Deimos. And the reason why they look so strange and sort of potato-shaped is because they're relatively small, and they haven't compressed into a spherical, basically, structure under their own gravitational force. So they're probably captured asteroidal bodies that currently orbit the planet Mars. But one potential architecture or use of these moons is to use them as a telecommunications relay point, right? Where you actually set up satellite dish, you could think of, on the surface of these moons so that people or rovers on the surface would communicate to a constant telecommunication source on these moons, which then communicates back to Earth. That's another way of doing it. That's a potential architecture that you could use. And we also think there may be materials that we could mine from these moons, whether it be minerals that are useful to us for construction or even water for future surface missions. But another important scientific finding is related to water on Mars. So I kind of gave it away, but we have found water on Mars. Here's an example of some of the water that we found. This is actually a picture taken underneath the Phoenix lander, which was landed in the mid-2000s. And that white region that you see there, which was exposed as the Phoenix lander was coming into land, its engines were pluming towards the ground, kicking up all the dust in the soil and exposing this white region beneath. And what this actually is salt water ice. So it's like a brine. So we know that closer to the polar regions, there actually is a lot of frozen subsurface water. And this is another picture that you can see that's been taken from orbit with our Mars Reconnaissance Orbiter. So we do know that there is actually water there, which is important, because that means future human colonies could use it for drinking, washing, growing plants, that type of thing. So now, who thinks that there's actually water flowing on the surface of Mars today? You're right. So this picture that you see here are pictures of water which is actually seeping out of the cliff faces on Mars. Because Mars is rotated on its axis, as the planet goes around the sun, it heats up and it cools down. So if there are frozen subsurface aquifers, they can melt and then seep out. And that's what we see here is seasonal flows coming off the sides of these cliff faces. And we've seen them again and again and again using high-resolution imaging from the Mars Reconnaissance Orbiter, which is a spacecraft which is in constant orbit around Mars and takes high-resolution images. So this, once again, is a really important finding because it means that there is water. It means that there is water accessible if we were to need it for future human needs. And it means that there could be stuff in that water. But until we actually are able to go sample it and take a look at it, we won't know. So that's another potential future mission where we would take a rover and have it access one of these sites so we could make compositional measurements of what's actually in that water. So the big challenge, however, for almost any mission that wants to land on another planet with an atmosphere is developing the technologies to be able to get yourself safely from exoatmospheric all the way down to the ground. And so landing on Mars actually has been a huge challenge. It's only been done 7 times successfully to date. The very first one was the Viking landers in the late 1970s, and you can imagine what an amazing engineering feat that was, right? We didn't really have sophisticated computers at that point in time. We also had very little knowledge of the Martian atmosphere. It was done again in the late 1990s with the Pathfinder rover, which was kind of a resurrection of the Mars program between the 70s and the 90s. It was done again in the early 2000s with the Spirit and Opportunity rover. Opportunity rover is still driving, actually, to this very day. So that was an amazing engineering feat to have something that could last for so long. Then the Phoenix lander, which was a landed platform as opposed to a rover. Curiosity in August of 2012. And then we have 2 missions coming up. There's the European ExoMars mission, which is actually launching in October of this year. So I hope you guys are all familiar with that landed technology. And then the InSight mission, which is going to land to make measurements of Mars quakes in 2018. And then, of course, an interesting aside is that the Beagle mission, although it was lost when it initially came in for its landing in the early 2000s, we later found it. So we did find evidence of where it landed on the surface. It means that their entry, descent, and landing technology suite did actually work. Just unfortunately, I think the solar panels weren't able to deploy, and it wasn't able to communicate, so they weren't able to do science with it. But that was an important finding for the European Space Agency, that was successful. And these are some of the images taken. This was of the Viking landers on the surface of Mars. This is Sojourner, and this is the Spirit and Opportunity Mars exploration rovers. And I think what I like to say about these images is how eerily similar they actually are to Earth. So even though it's another planet, it's another world away, there is so many similarities between what we have here on Earth and what we have here on Mars. Of course, however, Mars doesn't have an atmosphere. So if anything, it should motivate us to take better care of our own planet so we don't go the path that particular planet has gone. But in terms of how do we do it? So in all engineering feats, we tend to build on our prior experiences, which are called our lessons learned, and we turn to improve our technologies from mission to the next mission to the next mission. And so what you can see here is the very first rover, which was the Sojourner rover, which was about the size of a Tonka truck, which is a child's toy. And then we moved to a slightly larger version, which I would say was the size of a lawnmower, which was the Spirit and Opportunity rover. And then most recently, we moved to the size of something the size of a golf cart or a small car. And the reason why we've increased the size of the rovers is simple. If you were going to move your house from one house to the next house, would you do it on the back of your bicycle, or would you do it on the back of a truck? You would do it on the back of a truck, because a truck allows you to have a bigger wheelbase, you can carry more equipment, and you can also traverse more complicated terrain. So as we increase the size of the rover, we increase the capability and the size of the scientific payload, and we increase our ability to drive over more difficult terrain, which may be more interesting from a science perspective. And so that's the reason why we've increased the rover size again and again, not just because Americans like to drive big cars. That's not it. But then I always like to give people a reference example of how big the Curiosity rover is for scale. So you can see here, relative to the police box. So it is actually quite large, but unfortunately, it probably can't fit in sideways, so it's not going to be able to go in the TARDIS anytime soon, which is a bit of a disappointment. But it is pretty amazing how we can increase these technologies, and each time we do it, we get better at landing the system, at driving the system, at communicating with it, and then getting even more and more science data. So what is the purpose of the Mars Science Laboratory mission? What is the purpose of the Curiosity rover? So it's actually to assess prior, past, present habitability of the surface. So it doesn't actually look for life, but it looks for whether or not the building blocks of life, the environment for life, either existed in the past or currently exist on the surface of Mars. And we do that by making several scientific measurements, which I'll talk about a little bit more. But we're trying to assess the biological potential. We're trying to assess sort of the geochemistry of the planet. How did things form? Do they all form volcanically, or do they also form in the presence of water? And then we're also trying to assess what the surface radiation environment is, because one of the most difficult things for organics, as far as we understand organics, is their susceptibility to radiation. And so we know that radiation in space is quite bad. We know that radiation in deep space is very, very bad. So what is the radiation like on the surface of Mars? So we've never actually made that measurement until this particular rover. And so that's really important to understanding, is it so harsh that everything should have been destroyed based off of our current knowledge of organics, DNA, and radiation interaction? Or is it not so bad that, number one, maybe things can survive there, and also how much shielding do we have to bring with us to be able to support people living on the surface of the planet? So probably the two biggest challenging things to send people to Mars is, one, developing the technologies to land something so large, and two, being able to survive in whatever the radiation environment has to be. So those are both technology challenges, but you need to have the data to understand what your requirements are to derive the technology to be able to facilitate it. So those are the reasons why we've put the specific suite of instruments that we have on the back of the Curiosity rover, which is essentially a robotic geologist. So then the next question becomes, you're going to send this rover, where are you going to send it? You have to actually pick a landing site. And the way you pick a landing site is a combination of, can I actually land there, and where do I want to land? And so what we do is we work with the science community. the Mars atmospheric science community and the Mars geological science community. And they hash it around. They've argued for probably about 2 to 3 years as to the best site to go to. And they finally down-selected on Gale Crater. And the reason why they selected Gale Crater is because they believe, at least from orbital images of it, that it probably was the site of an ancient water body, whether it be a dried-up lake bed, dried-up riverbed, but they actually thought that. And where better to look for evidence of past life than in the base of a water body where sedimentary rock layers would form and you would see the history over time. So that's the reason why we selected Gale Crater from a science perspective. Our challenge then was to ensure that the engineering system could land there accurately. And from a scale perspective, this crater geometry, we would have to land somewhere between this mountain in the middle and between the crater edge on the side. Because if you didn't, you would either smack into the crater wall or smack into the mountain, and then there would be no mission moving forward. But also for reference, this is kind of like a Mercator projection of Mars. So MSL landed in Gale Crater. Mars Exploration Rover B is currently over here in Meridiani. It's a very large difference between these two things, so unfortunately they'll never be able to drive to meet each other. I have been asked that question before, so they'll forever be apart. But if you've seen The Martian, people have seen The Martian here, I assume the movie, you can utilize those parts for a future human mission. So I was able to guess within 2 pages of that book that that was what they were going to do. But we can have a discussion about that later if you're interested. So this is Gale Crater. So this is the home of Curiosity now, and this is the landing site that we selected. And what you see here is sort of a black ellipse. And what this black ellipse is something called our landing ellipse. This basically, we've designed a system that we could land in an area which was 20 kilometers long by 7 kilometers wide. And that happens to be very tricky when you're trying to land in a space, which is basically, so this is what I'm using for reference. So this is the distance between London Heathrow and central London is roughly around 20 kilometers. So we had to have the ability to have a precision so that we knew we could land in that area all the way from Earth going out to Mars. And so that drives the design of our engineering system. Because if you didn't, you have Mount Sharp here, which would be game over, and you have the edge of the crater wall here, which would also be game over. And then we also knew that we wanted to be able to drive to the lower reaches of Mount Sharp, because we could see from orbit that's where we had some interesting rock layers that we wanted to be able to interrogate it. But because of the uncertainties in the atmosphere, because of the uncertainties in a whole variety of engineering parameters, you can't get yourself to a pinpoint location. You can only get yourself to this kind of ellipsoid location. So we did our best effort to be able to drive down or drive up the accuracy of that. So another way of viewing that is a bullseye. And so what you can see on this outer ring here is the landing ellipse size for the 1976 Viking mission, 174 miles. We had to go from 174 miles all the way down to 12 miles. Apologies for going between English and metric units. So that's where the challenge was improving the accuracy of our landing system to be able to land in that very small space, thereby facilitating having access to Gale Crater. Because if you had a landing ellipse the size of Viking, you wouldn't know whether you would land here or over here on landing day. So that wouldn't work for you. So that was essentially the challenge associated with it. So I wanted to talk through a little bit of this video. So this is the entry descent landing sequence. Landing up through a planetary atmosphere utilizes the atmosphere to produce aerodynamic drag. So you come in at 13,000 miles an hour. You decelerate roughly from 13,000 miles an hour to around 1,000 miles an hour on a heat shield. You then decelerate from 1,000 miles an hour to around 250 miles an hour on a parachute. Then you actually can't go any slower on the parachute. You've hit terminal velocity. And so at that point, you actually cut the parachute away. And then you descend the rest of the way, slowing yourself down using retro rockets, firing towards the ground. That's the way you dissipate the energy. And we had a total of 8 retro rockets actually going towards the ground. When we were around 60 feet above the surface, we started to lower the rover on a tether. This is called the sky crane maneuver. And we can talk about might be good for a question and answer session if you want to know why we chose to do certain things that we did. But we primarily do it to increase the distance between those retro rockets and the surface of Mars, because they end up kicking up a lot of dust and sand, and you'll see that in a moment. It also allows the rover to be the landed platform. So instead of carrying an airbag, which you have to carry all the way down to the surface, you just touch down on your wheels and you're ready to go. So what makes Mars actually nice from a landing perspective is that you don't have to carry as much propellant with you because you can actually use the atmosphere to slow you down. So anyone has put their arm out the side of their car when you're going down a motorway and you feel the force on your arm, that's aerodynamic drag. So we use that principle to slow ourselves down to take out roughly 99% of the energy coming in. The rest does have to be taken out using retro rockets, but the atmosphere does help you in that sense. The problem, however, is that, when you rub your hands together, they get very warm. They get warm because of friction. We also experience friction with the atmosphere, and that friction with the atmosphere would make anything burn up. So we use a technology called a heat shield to absorb that energy so the rover inside of it doesn't heat up and doesn't get damaged. So that's the traditional architecture between how you land in a planetary atmosphere. And so this is a two-dimensional view of that entry, descent, and landing sequence. And so it does start out here at hypersonic speeds, 13,000 miles an hour roughly, gets you down to supersonic speeds, which is Mach 2. We then deploy the parachute, going from Mach 2, which is around 1,000 miles an hour, down to around 250 miles an hour, and then we switch over to the power descent sequence. And through all this, we have to manage our speed, manage our location, manage our altitude, and we have to know that. And we don't fly this back from Earth because the time delay between Earth and Mars is roughly 14 minutes in the worst case scenario. So this is all done autonomously by the spacecraft, by having knowledge of what the atmospheric properties are, and then making measurements using an accelerometer to tell it basically what its velocity is, and then going through a sequence associated with that. And so this is the overall architecture, and it's broken up into different phases. And so I'll talk a little bit more about the parachute phase, just because that's what I worked on for several years. So what is a parachute, and why do we use parachutes on Mars? So what a parachute is basically a textile device. And if I could have, are there any kids in the audience? Could the kids come down? I just need 2 or 3 people. You can help me hold it, so you can show everybody what it's like. So what a parachute is it's incredibly lightweight, but it's very, very strong. See if we can go out front here, so you can kind of show it for everybody. So you can hold this end, and then you can hold this end, and then I'll pull it, and you can hold the end in the middle here. It's got a little bit snagged. And then we can kind of open it up together. And so what you can see here is it weighs almost nothing. It occupies almost no space, yet it generates a lot of aerodynamic drag. And so the parachute that we used for MSL was 21.5 meters in diameter. So that's 60 feet in diameter. It's huge. And so you can see from the picture there the size of the people, the size of the parachute. And the reason why the parachute has to be so big is because the atmosphere is so thin, which means a bigger drag area so that you can slow yourself down. And the reason why we like a lightweight device is because when you go into space, you usually don't have a lot of mass available to you, right? You're otherwise more mass, more propellant. So you want something which is as light as possible. And so you can see, you should touch it here and see how thin it is, right? It weighs almost nothing, at least to the touch. And the same thing with these lines, which are called the suspension lines. They're also very thin, and they don't weigh that much. And so that's the primary reason why we use it, because it's basically using the atmosphere for free. And we use modern materials, which allow things to be incredibly strong versus more ancient materials. Like if you had a metal parachute or something, you wouldn't get much benefit from it. So that's what it is. And then also, because it's so thin, you can pack it into really tiny spaces. And so when we pack these parachutes, they actually approach the density of wood. So it gives you an idea of how tightly we can pack them, how little space they actually occupy in the vehicle. Yet when they open up to fill a room probably about 6 times the size of this. So this is a scaled version of a parachute. This isn't the full-size version for MSL, but it does have a very similar design. And then what you also note here is that there's an opening here. So this is called a gap. This region at the top here is called the disc, and this is called the band. And so the reason why we have a very specific parachute design is because of the aerodynamic environment that we found ourselves in. It's actually a supersonic aerodynamic environment, and it gets really unstable. And the way you control sort of the stability and the flow is by having this gap here, which kind of allows the atmosphere to flow through it so it doesn't collapse too much, but I'll show you that it's kind of iron. So I think I'll put this back, and then I'll let you touch this other thing since you're down here. So the other thing that is important is by having really strong materials. And so one of the strongest materials in terms of lightweight materials that we know about is Kevlar. So you can touch this one too. So Kevlar is a very special material. It's a polyaramid fiber, and it has an incredibly strong strength-to-weight ratio. So this Kevlar cord that you see here, you can basically hold thousands of pounds off of the end of it and it won't break because they're engineered materials. So one of the neatest things about engineering is that you're able to develop these amazing lightweight, incredibly strong materials. And of course, Kevlar is the same material which is used in bulletproof vests. So that gives you an idea of how strong it is. But this is more in a textile sense so that you can sew it and you can work with it. But I think we can probably pass it around to the audience. But I think that's kind of what I wanted to show. So thank you for coming down. And I'll give you stickers later for coming out. So. So I'll pass it around so you guys can see what it feels like. Thank you. A little airplane, yes. And so that's essentially why we use a parachute. And so the scale of the MSL parachute, you can see here, it's incredibly large. I took sort of an international regulation football field, and you basically could fit a total of 6 of these MSL parachutes. And that's how big it actually is. So then the question becomes, well, how do I design the parachute and test the parachute to make sure that it survives on Mars before I get there? And we actually do a lot of testing. That was one of the reasons why I took the job, because I love testing out in the field. And this was our very first successful test of the MSL parachute. We actually put it on a helicopter. We take it up to around 3,000 feet altitude, and then we deploy it. And this allows you to match the same load that the parachute sees in an Earth-based test as it would see in a Mars environment. The difference, however, is that the atmospheric pressure and density on Earth is much higher, which means that you don't have to take it up to as high an altitude. On Mars, the atmospheric density is much lower, so you end up having to have it go faster to match the same aerodynamic load. But the real challenge is that parachutes on Mars behave very differently. And the reason for that is that they deploy in a supersonic, low-density environment. So this is actually what it looks like when a parachute on Mars deploys. It's very, very different. So you see how it collapses and inflates and collapses and inflates. It actually starts to get a tear in it. So this is an example of a test that was done probably in the 1970s, I think it was. And they were able to take this parachute up to around 150,000 feet altitude on Earth, attach a rocket to it to get it up to Mach 2, and then deploy it to be able to experience the exact same conditions that it would see on Earth as on Mars. It happens to be very expensive to do these kinds of tests, so we weren't able to do that for MSL. So the space program budgets have gone down over the years. So what that means is that we can't just test everything how we would like to test it. We end up having to come up with much smarter, more cost-efficient ways of doing it. So what we decided to do was use our knowledge of fundamental physics, aerodynamics, and computer simulations to be able to understand how is this parachute going to perform on Mars? How are we going to make sure that it's strong enough? And so we first started off with a computer simulation. And so this is something called computational fluid dynamics, where we represent the flow field around the vehicle. So the MSL vehicle is basically here, and it's sort of trailing behind it is the parachute. And so what you see in front of this is a bow shock. This is because we're in supersonic flow. And so we generated a simulation to understand how the flow field of this entry vehicle would affect the parachute, and then what would the pressure distribution be like, how much load would it experience. But when you do a computer simulation, the simulation is only as good as if it's correct, right? And so just by doing a simulation isn't enough. You have to validate your simulation. So what we did to validate the simulation is by building little subscale parachutes, and so we've got one demo coming up, but I'll show you an example of a subscale parachute. So this is actually something we developed for the human space program, but you can get an idea that this size parachute is roughly 3% of the size of the full-scale parachute. So if you build an identical model in terms of geometric shape, you should get similar aerodynamic performance. You can then put this model parachute in a wind tunnel at the appropriate conditions. So there's actually wind tunnels where you control the density, where you can control the pressure, where you control the atmosphere, you can control the speed. And so what we did was we built little subscale parachutes, put them in the correct aerodynamic environment, see how they behaved, made measurements of them in terms of the total load on them, and then compared it to simulations to validate the simulations. And so we do have one. Is Andy, my colleague, is up there. Andy Cowley is, I would say, Britain's foremost parachute expert, and he has come to help me with a demo. So this is an example of what the parachute looks like when it's deflating. So, well done, Andy. And so, what you can see here is a subscale DGB. So this is very similar to the one that we tested for the Mars Science Laboratory mission. So it's a little bit smaller than this one. This is roughly 3% scale of the full parachute. And what we did was we put this in a wind tunnel. And so in the wind tunnel, you have the vehicle, this is kind of like the MSL vehicle, rigidly mounted, and then you're basically flowing air through the wind tunnel. And so it's flying as it would in actual flight. And then you're also making measurements of how much load does it experience. Is it collapsing and inflating like we had seen before? And I'll show you some of those measurements. But it's amazing how much you can figure out by doing sophisticated computer simulations and then validating them by excellent experimentation. And that's kind of what this institution is about, right? Like experimentalist Michael Faraday, that's what he did. We did experiments, and then he figured out how things worked based off of those experiments. And that continues to the present day in just about every field of science and engineering that you can find. And so this is an example of the wind tunnel measurement that we did. This little parachute flying These video that you can see actually has been slowed down so you can see it. So this whole cycle that you see looping actually happened in the order of milliseconds. So it happens incredibly fast. The eye can't see it, but we can use high-speed imaging so we can see what's going on. And you see the little dots on the outside of the parachute? This is basically a motion capture technique. So we're taking many, many images of this video, we're capturing them on sub-millisecond intervals, and then we're reconstructing the motion of the parachute using image processing, basically after the fact, to determine what the parachute shape is like, as well as making a measurement of what the parachute load is. And so this is how we can provide that same data set that super expensive high-altitude test provided, but at a much lower cost, and a much shorter time scale, so you can actually repeat measurements, like change the speed, change a whole variety of parameters, so you can learn even more. And in terms of the fundamental physics of what's going on, we also used a technique called Schlieren, to take a look at what's going on in the supersonic flow field. And so the computer simulation I showed you before, you could see the bow shock moving back and forth. This technique allows you to see density contours in the air in the wind tunnel, and so you can see the bow shock is moving forward and it's collapsing, it's moving forward and it's collapsing. And so this is the physics behind what happens to parachutes in supersonic flow. And so we validated the physics of what was happening, we validated our simulations, and then we were able to design our parachute to be strong enough, perform well enough, so we could send it to Mars. And so even though we did full-scale tests to do structural testing, we also did little subscale test to verify how it would actually perform in that difficult, dangerous supersonic environment. And we were successful, and of course we did land on Mars, so it did work. And I do like to show this picture because sadly, and one of the reasons why I do a lot of these lectures, basically around the world and oftentimes mainly to students, is because we do need diversity in the engineering science fields. And this is an example of where there is insufficient diversity. And sadly, aerospace engineering, electrical engineering is pretty underrepresented from a female perspective. So I would encourage you to talk to your daughters, your sisters, to get involved in engineering because it's a great job. The STEM fields are kind of amazing. They pay really well. They're intellectually stimulating, and I would like to work with more women as well. Although I love my male colleagues as well, but it is important because, and I do like to say this, is that if all you had was a carbon copy of everybody, like everybody was I guess clones of each other, you would come up with one idea, right? So you have to have diversity in the workplace to have a diversity of solutions. You can come up with a better product at the end of the day. So it's really important, whether it's ethnic diversity, religious diversity, men versus women, different countries. Those different backgrounds that you come from allow you to come up with a different way of solving problems, and we work together, actually, a very diverse team in that sense, for the overall entry to set landing sequence, and I think that's really important. So just to drive that point home. So I wanted to talk a little bit about Curiosity in terms of the rovers. You can see here, Curiosity is the size of a small car. Curiosity does also have a difference between the prior rovers. The prior rovers used solar panels for power. Curiosity uses an RTG. It's a radioisotope thermoelectric generator. So it uses the decay of plutonium-238, the heat associated with that, and converts it into electrical energy. And so what that means is that you have constant power, not just power when the sun is pointing on you. So that allows you to operate over longer periods of the day. It allows you to operate in places, further away from the equator. It allows you to do more science, basically. So that's the reason why we selected that particular technology. So that was different from this rover to the next rover. And then Curiosity, of course, had a very sophisticated mobility system that you can see down here, which allows it to traverse over rocks up to 0.5 meter in size without tipping over, without having any problems whatsoever. So once again, that big wheelbase is that big capability to take you to really interesting places. So the rover is a robotic geologist, and any geologist wants to be able to see as well as touch things, and so the rover does have eyes. It actually has a whole series of cameras. Some of those cameras are actually used for navigation, for hazard avoidance, so we do not drive the rover with a joystick. We give it a set of commands and tell it we want you to go there today. It has to do that safely, and it does that by collecting images with its cameras and doing, sophisticated algorithms to make sure that it isn't going to have a problem in terms of, going into a dangerous location or driving to an area that it couldn't drive. So that's what some of the cameras are for. And then others of the cameras are used to collect panoramic image of its surrounding, as well as microscopic images of the rocks that it's analyzing for scientific purposes. So one very important instrument is the SAM instrument, Sample Analysis on Mars. It's actually a mass spectrometer. So a mass spectrometer allows you to determine both elemental and molecular composition. So this is how we're able to look for organics. And organics, of course, are the building blocks of life. And this is probably the most, it's a very heavy instrument. It's a very sophisticated instrument. And it does allow you to make the determination of whether or not organics are present. And one of the ways that it does that, and this maybe only Americans will appreciate this, but an easy bake oven. So it basically has a little oven that heats up samples. And when the sample's heated up, they release a certain spectroscopic signature, which then you can associate with molecular composition, elemental composition. And so this is probably our most sophisticated instrument on Mars. And so we have another instrument which has a laser, and that laser also, it's called LIBS, laser-induced spectroscopy. So what does a laser on Mars look like? Not quite. I'll show you what it actually looks like. But everybody loves that. But this is a high-power laser, right? So if you were a astronaut on Mars, you probably would not want to stand in the way because it would burn a hole in your spacesuit, for example. Because you have to use this laser to vaporize rocks. And when you vaporize the rocks, they then generate this spectroscopic signature, it's basically a plasma, which allows you to determine what the rock is made out of. So we have two ways of doing it, mass spectroscopy as well as laser-induced breakdown spectroscopy. So if you were on Mars, can you imagine not being able to touch anything? That would be terrible. Somebody wrapped your arms around your back. So Curiosity does have an arm. The arm has many different purposes, but it allows it to go and touch rocks. Because if I put a tablecloth on top of this table, would you know that it was made out of wood? You wouldn't, right? You have to be able to remove the tablecloth to figure out what the table is actually made of. So what the arm has at the end of it is a brush, a drill, so it can actually interrogate the subsurface to determine what the composition is, not just the surface layer, which could be quite different because it could be deposited by winds and things like that. So the arm is very important for making measurements of soil composition of things, not just the surface, but the subsurface material. So moving forward, we built the entry, descent, and landing system. We built the rover. We packaged them inside of the aeroshell, which is the vehicle which contains the rover, which has the heat shield, which allows it to withstand, and the parachute packed inside there. So who thinks it takes more than a year to get Mars? Less than a year? Yes. It takes roughly 9 months, so it's the gestation period of a human baby, or it's a school year for at least American kids, maybe a little bit less than a school year for British kids, but it's not that long, actually, if you think about it, right? Of course, maybe for the kids, it seems like a long time, but for adults, it's not a long time. And so we basically launched in November of 2011, got there around 8 months later, so in August of 2012, it was landing night, and it was nighttime, Pacific time in Pasadena, which is where we operate the rover from, and where a lot of the work was done. We had a very unique opportunity, this mission, where we attached a camera to the underside of the rover, so that during the landing event, all the way from entry, heat shield separation down to the ground, we could actually see what was going on. So that is the next video I will show you. And this is kind of amazing. It's the bird's eye view. So what you're seeing is the heat shield falling away in the distance. And the reason why we remove the heat shield when we can is because it reduces mass, so it then reduces the amount of fuel that you need to slow yourself down. It also allows our radar to look down towards the ground. So the radar is basically, it sends an RF pulse out, it gets back, there's a total of 5 beams. It allows you to determine what your altitude is, what your vertical velocity is, and what your horizontal velocity is. And that information goes into a closed loop algorithm to help fly the vehicle safely towards the ground. So the other thing to notice is that you can see it's kind of rocking back and forth. And the reason why it's rocking back and forth is because this is a rover hanging underneath the parachutes. If anyone has skydived here, you know that you don't just fall straight down, you kind of move around a little bit. So that actually shows you what the dynamics under the parachute is. And you can see here, these darkened regions are probably ancient volcanic deposits. Here are some impact craters on the ground. These are all craters within the Gale Crater. So at this point, we're just looking at Gale Crater coming down. And then what you'll see in a few moments is that the rocking has stopped. Now it seems to be moving to the side. That's because it has been the parachute has been cut off. It's now under those retro rockets. And the retro rockets can actually be fired differently from each other to vary your thrust and vary your trajectory. So what you're seeing here is you're getting closer and closer to the ground. We're starting to get this interaction with the soil. You can see it's actually getting kicked up, and that's because those rocket engines are so strong. This is the wheel falling into the view. This is the start of the sky crane maneuver, and it's getting closer and closer to the ground. Now you can't really see the ground because there's so much interaction with the soil. But at this point, essentially, we've landed. So this data set got downlinked, a couple of days after landing, so we didn't get it right on landing night. But when the rover had successfully landed on the surface, its primary job was to send us telemetry saying everything's good, and an image of where it landed on the surface. And we're all anxiously waiting for this image to come down. And so this is the first image that we saw. So this is the shadow of the Curiosity rover. It looks like a transformer for anybody who likes transformers out there. And then what you can see here in the distance is Mount Sharp. And so it's pretty amazing, right? So it's hurled its way all the way from Earth to Mars and safely landed on the surface of the planet. So you can imagine we were all ecstatic that this happened, and it went off as planned. And here's another more colorful image of Mount Sharp. And this is also a better shot of sort of the striations that exist on the side of Mount Sharp. And what I'd like to show here is if anyone has been to, the American desert near Nevada or, anywhere like that in Arizona, it looks just like Earth. And I think that is kind of amazing. Of course, there's no air there, so you wouldn't last long once you stuck your head out, but it does look like Earth. And I think that's kind of an amazing thing, that even though these are worlds apart from each other, they have so much similarity to our own home. And I would say our greatest fear, of course, was that everything would happen. We would land safely on the surface, but those tethers wouldn't get cut, and then the rover would be like dragged across the surface of the planet. That didn't happen, obviously. Everything went as planned, so we were rather ecstatic. And so if you are an engineer, you are most likely a nerd, and you want to know how good your calculations were, this red ellipse you see here was our calculated landing ellipse, like I mentioned before, and this white box is basically where we landed. So that means, number one, our calculations were great. And that also means that we were on so that means our calculations of drag coefficient, of atmospheric properties were pretty much spot on. So that means we pat ourselves on the back that we did a good job in addition to other things. So now, other thing to point out here is this is where we landed, but this is where we wanted to go. So we had several kilometers that we would have to drive in order to reach that eventual location, which is our target location. So, and just so you know, the rover moves about, this is its top speed, basically. And that, however, doesn't compare anything to when the science community says, nope, stop there, stop there, stop there, stop there, to make measurements. So it takes a long time to be able to drive from point A to point B in this particular case. And you can, if you want to ask me questions why we drive so slow, there's actually a reason for it. But nevertheless, we landed where we wanted to land, and then we started our traverse towards the final location, making science measurements along the way. But as you can imagine, after landing that, we had a wonderful party. I think we were all out until 6 o'clock the next morning. And we were dancing and singing and stuff like that. And then we got this picture on our smartphones. And what this picture is a picture taken by the Mars Reconnaissance Orbiter. It was actually positioned into place to capture the parachute and the rover descending on Mars. And of course, this made me incredibly happy. So this is basically a picture of the descent on Mars. And what you can see here is the parachute is nicely inflated. There's no apparent holes in it. And of course, this is the back shell, which has the rover underneath it. So we'd never been able to take an image like this before. So it was pretty awesome, right? That we have enough assets around Mars that we can take pictures of our landings. So for PR purposes, just kidding. It's good for engineering purposes too. So now, if you were to buy a car, what's the first thing you're going to do before you actually buy it? You're going to go on a test drive, right? So the very first thing we did with the rover after landing wasn't start the science mission, but you have to do a test drive, make sure all the systems are working well. So you can see we drove it around, drove it back and forth, and I always like to point this out. You see this tread on the tires here? This actually says JPL in Morse code. So it was our way of getting our signature there, because when there's an alien race in the future who goes to Mars, we go, oh, look, JPL was there. They may not know what that is. It might be long gone by then. But anyway, that was our way of, and it actually has a secondary purpose, which is a fiducial marking. So by knowing the exact geometry, and when you take images, you can use that as a calibration target, basically. But it also says our name. So I love this picture, and so this picture is what a dried up riverbed on Earth looks like. The one on the left is where we landed on Mars. And so I'm not a geologist, but when geologists do look at these images by looking at how the rocks are formed together and how they're sort of worn on one side, they're able to confirm that they were actually formed in the presence of water. We have several other scientific measurements that corroborate it. But what we do know is that the Curiosity rover landed in the base of an ancient water body, which was about knee deep. So in the past, in the ancient past, obviously the water is not knee deep now, but just put yourself into that mindset about where Curiosity is driving around, that there actually was sort of a lake on Mars there, which is pretty exciting, I think. Now, we have had some very important findings over the course of the past several years of driving around. This is another example of what the surface features look like. We found the presence of phyllosilicates, which can only form in the presence of water. And we've also confirmed that the soil is actually neutral in terms of its alkalinity, which means it's not basic, it's not acidic. And that's very important from a formation of organics perspective, life forms perspective, because our existing experience on Earth suggests that neutral soil is much better for supporting life than acidic soil, which makes sense, right? But that's an important finding, because other places that we visited on Mars have been acidic. So this is a location, because of its water body nature, where it was not acidic. So that was a pretty important finding. So some more things that the rover did, it scooped the soil. So what you can see here is it uses this scoop to collect samples that it then puts inside the instrument into the EV bake oven and gets it to work. And then we did a lot of using of our laser, our LIBS instrument, and as you know, that's obvious, right? Curiosity killed the cat. Now, I am a cat person, so I don't mean to be heartless, but it's just very funny, and it had to happen. Okay, so so that is kind of funny. But so now what does the laser really do? It's not as impressive as that, as killing a cat, but that's not impressive. But so this is what it does. So if you were on Twitter after landing, you heard people with the hashtag pew, pew, pew. I don't know if you saw that or not. That was the LIBS instrument going. So what it does, it burns a hole in a rock. So this is the before, after loop. And when it burns the hole in the rock, it vaporizes the rock. It generates a spectroscopic signature that you can see here. And so each one of these lines is associated with a particular wavelength. And we know that that's actually a fingerprint for iron, magnesium, silicon. So this is sort of a elemental fingerprint for what the composition is of the soil on Mars that we analyze. So it's a very sophisticated but very robust way of determining what the composition is. And of course, you have to have a weather station. Curiosity also has a weather station. And so it has the ability to measure winds, pressure, and temperature. And so the interesting theory here, of course, is this is the diurnal variation, right? So it gets colder at night. Warmer during the day, colder night, warmer during the day. So you can see the correlation between temperature changes, solar changes, as well as pressure changes. And that's also a very pretty looking picture, I think. So this is another important measurement. You won't make much of this hash, but now we do have Mars surface radiation measurement. It's not as bad as we thought it was going to be. It still obviously is good for human beings, but now we have an ability to know what we have to attenuate if we were to send people on the surface. It also gives us a better idea of what Earth-based analog life forms could survive with that kind of surface radiation level. And the other thing to note is that having an atmosphere actually serves to attenuate radiation. So we can see variations in this radiation signal which actually correlate with the surface temperature because the pressure or the density of the atmosphere is changing during the course of the day. So this gives us a ton of information which we have never had before. And then another really important measurement is of organics. And so we did have confirmation of methane on Mars. And so methane is really important. It's an organic. It can only come from one of two sources, either geological or biological. So geological, coming out of the rocks, volcanic processes, and biological would be, cows produce methane in their gut, which is bacteria. So that's why we don't know until you have to make a more sophisticated measurement to get you an idea of whether or not it's biological or geological in nature. So that we don't know. But having found it there is really important because methane has a very short lifetime, which means it had to have been produced relatively recently, meaning in the past less than a million years. So that's actually a pretty significant finding. So now, of course, there is no car wash on Mars. So what that means is poor Curiosity has dust everywhere underneath its belly pan and then on its wheels. And another interesting aside from this, though, is that just like you want to change your tires for your car, unfortunately we can't. So our wheels have one shot at it, and they are experiencing some wear as a result of going over these big rocks, which is to be expected over time. But there is no tire changing station, no AAA out there. So is there intelligence on Mars? I would argue that there is, right? So we have Curiosity, who's quite intelligent, and then we're behind Curiosity in terms of telling it what to study next. And I think that's kind of exciting. So I've got one video I wanted to show you, which is a compilation of all of the images that Curiosity took over the course of the first year. So that's the very first image. And so you can just see how busy it is, right? Every day, all it does is work, collecting scientific information. And there you can see it using its arm. And it's just kind of amazing, because it really is a geologist, but it's a robotic biologist, and of course we're driving it as opposed to a person actually being there. But from our perspective, it actually is very similar to us actually being there. So it's super exciting, and I can never get over the fact that it looks like a transformer. So just sharing that with you. So what is in the future? So the future is actually bright. We want to send human beings to Mars, hopefully within our lifetimes. And we need to enable the exploration of other worlds, and going to Mars will do that. So that would be the first stepping stone sort of for humanity going out into the stars beyond low Earth orbit. So in terms of the future, we would need to be able to live on the surface. We have to develop the technologies to land on the surface. We have to develop a rocket which will launch off of the surface. We have to develop habitation modules where we can survive the radiation environment, have the ability to maintain a pressurized environment for many, many years. So what I would like to point out, though, is for any of the young people in the audience, the future is basically what you would be doing as engineers and scientists and mathematicians if you want to go into the aerospace fields, because this really is the push, right? So up until this point in time, it has been sending robots to Mars, and we're going to continue to do that, continue to collect more scientific data. But what is going to happen in the future is sending people there. And then all of the technology that gets developed is all done by engineers, whether it's aerospace engineers, electrical engineers, chemical engineers, computer scientists. Those are the people who do the work to make this happen. So that's why it's super exciting. So that's my plug to you. So would you want to live on Mars? These are some artist conceptions of what it might look like. And I think it is a real thing of the future. And it's really just a matter of time and a matter of money and ingenuity for us to get there. And I think the last thing I want to say is, who's the future of space exploration? You really are. And so what I like to do is go and talk to students. So I have my students that I teach at USC, and then I talk to students in the local community, I talk to students everywhere to kind of motivate you to do the same, because this is a super fun job. It's incredibly exciting. Really nothing does compare to it. There isn't a day you go to work where you're not challenged, excited. Sometimes it's scary, sometimes things go wrong, but you're the person who's there to fix it, right? So that's kind of important. So that's my motivation and to help you study. And so in terms of what's over the next horizon, we don't really know, but we do know that there's several more Mars missions planned, so that's for sure. And also to point out, and of course this is not a US audience, but Curiosity took over 3,000 people, scientists and engineers, to design it, to build it, to test it, to operate it. 12 countries were involved that either contributed instruments or science investigations. All of the images that we take are returned to Earth almost immediately, available for everyone to look at. And a really interesting thing that most people know about is that finding of water flowing on Mars was in October of 2015, and it was actually discovered by a student at Georgia Tech. So these images, which we make available, any scientist, any student can analyze and make it a part of their research program. So, yeah, because it's our rover. That's kind of how we like to say it. So I am happy to take questions for the remainder of the talk. I think we have 30 minutes. Thanks.